Howdy, welcome to another video on straight line graphs, the second in the series on straight line graphs. The first lesson served as more or less just a recap of the skills you should be familiar with already at the GCSE. Today we're going to ramp up the difficulty somewhat and have a look at some proper AS style questions, including some actual past paper questions that have come up in the past. But before we get on to those, let's have a look at the warm-up questions for you to try. 4 of them, almost as ever. Try these first without using the video, play the video to verify your answers, and make any corrections necessary afterwards. So let's have a look at question 1. Question 1, we have to calculate the gradient and the y-axis intercept of this straight line given below. So the best way of doing that is to rearrange into the form y equals mx plus c. So if we just leave the 3y as it is and add the 7x and subtract minus 13, we rearrange it into this form. 3y equals 7x minus 13. If we then divide through both sides by 3, we get that y equals 7/3 x, or 7x over 3, minus 13 over 3. So the coefficient of the x, when it's written in the y equals mx plus c form, that tells us the gradient. In other words, the gradient is 7/3. Now the y-axis intercept in this form is the constant at the end. In other words, the y-axis intercept is minus 13 over 3. So all we need to do now is to just write that down. So therefore, the gradient equals 7/3, and the y-axis intercept equals minus 13 over 3. And that's question 1 out of the way. Question 2, we've got 3 points, A, which is minus 3, 2, B, which is minus 1, P, and C, which is 5, 18, and they're collinear. Find the value of P. If you're with me for the last video, or from last lesson if you can recall, we mentioned this word collinear. All it means is if 3 or more points, in fact, any number of points, if they're collinear, it just means you could draw a straight line going through them. So that means that if 3 or more points are collinear, then any line segment joining any 2 of any number of points on that line have to have the same gradient. If you've got 2 points on any straight line, if you take any 2 points along that straight line, the gradient between them has to be the same. It's almost common sense, really. So what we can do is we can evaluate the gradient at AB, then take the gradient at BC, and then form a simultaneous equation and solve for P. So first of all, let's just think about the gradient in between A and B. So from first principles, the gradient is the change in y divided by the change in x. So at B, let's take this as our final and A as our original. So final minus original for y gives us P minus 2. And the same for the x-coordinates, minus 1, be a bit careful here, minus 3. So that gives us P minus 2 over 2, because minus 1 minus minus 3 is the same as minus 1 plus 3, which gives us 2. We then do the same for the line segment going from B to C and evaluate that gradient. So taking C as our final point and B as our original, the change in the y-coordinates from B going to C is 18 minus P, so the change in y is 18 minus P on the top. On the bottom, the change in x is 5 minus 1. So that gives us 18 minus P all over 6. And so because these points are collinear, the gradient from A to B has to be the same as the gradient from B to C. And so we can summarise this by saying that therefore P minus 2 over 2 must have the same value as 18 minus P over 6. So This is an equation we can solve. So what I'm going to suggest we do is we multiply both sides by 6 just to get rid of any denominators. So if we multiply both sides by 6, this becomes 6p over 2, so we get 3p over here. Minus 2 times 6 is 12. Divide by 2, that gives us minus 6. And on this side, the denominator just vanishes. We just end up with 18 minus p. If we add p to both sides, we get 4p minus 6 equals 18. Add 6 to both sides now, we get 4p equals 24. Final step, divide everything through by 4, therefore we know that p must equal 6. Question 3. We're going to use the answer to question 3 later, by the way, so I'll return to that point and mention it again later on. So question 3, this one has some importance later on. So find the coordinates of the point of intersection between the lines y equals 4x minus 7 and 2x plus 3y minus 21 equals 0. So there's a few ways of doing this. What we could do, we could solve simultaneously. We could substitute in. We could do a few things to work out these points of intersection. What I'm going to do, first of all, I'm going to take this equation here, y equals 4x minus 7. I'm going to substitute this value of y into this equation here. And so what we'd get is 2x plus 3 lots of y, which is 4x minus 7, minus 21 equals 0. So let's expand this out. So we get 2x, 3 times 4x gives us another 12x, 3 times minus 7 gives us minus 21. We had a minus 21 from before as well, so that equals 0. 12 plus 2x, or 2x plus 12x, gives us 14x. And then here, minus 21 minus 21, that's minus 42. We can now add 42 to both sides. We get 14x equals 42. Finally, if we divide through by 14, we see that, therefore, x must equal 3. So, now we know that x is equal to 3, we can sub this into y equals 4x minus 7. So if we now substitute x equals 3 into y equals 4x minus 7, we get that y, the corresponding coordinate of y, must be 4 lots of 3, because x is 3, minus 7. 4 times 3 is 12. 12 minus 7, that gives us 5. So x is 3, y is 5, so we've worked out the coordinates of intersection. So therefore the coordinates of intersection for these two lines are when x is 3 and y is 5. And so that's question 3 complete. Last for the warm-up, we have question 4. We've got 2 points that lie in a straight line, A and B. We have to show that the distance AB can be written in the form A root 5, where A is an integer to be found. So you don't have to do this, but my suggestion would be to do a little sketch of this straight line that goes through A and B. So what I'm going to do here is just pop on a straight line like so. Then we can think about for 2 points at either end. So let's call this point A, and this point at the other end, let's call that B. So what is A? Well, A is minus 4, 5, and B is 10, 12. Now we can return to, again, something familiar from GCSE. We can work out the distance between this line by using something you might have heard before. We can use Pythagoras. So if we were to apply Pythagoras to this, we can just take the horizontal distance from A to B, and the vertical distance between A and B. I've gone a bit too far there with that line, so let's just shrink that down slightly. There we go. And just apply Pythagoras by working out this distance and that distance, and then doing a squared plus b squared equals c squared. So in case it isn't now familiar to you, I'm just going to write down Pythagoras for the hell of it. Yep, we're going to use good old Pythagoras. So let's have a look at these x coordinates. So x at A is minus 4. It goes up to 10 at B. And so from minus 4 to 10, that tells us that this distance here has to be 14. So along the bottom, the distance we have is 14. So we can add this in now. So that distance is 14. Similarly, we can do the same thinking about the vertical distance. So from A up to B, A starts at 5 in the y direction, goes up to 12 for B. So 12 minus 5, that's an increase of 7. So using Pythagoras, for distance, which we just labelled C, could have labelled it anything, could have labelled it nothing. Distance C is going to be the square root of the other two shorter sides squared and added together. So that's going to be 14 squared plus 7 squared. Now if we read the question carefully, it does say show that. So I'm not going to just bash in these numbers on the calculator and see what it spits out. I'm going to show it carefully to the examiner step by step. So what's 14 squared? Now you could use a calculator for that. In fact, let's do that now. So 14 squared should be 196, I'm hoping. Yep, 196. And 7 squared is going to be 49. If we add those two together, 196 plus 49, we'd get 245. Our end game is we want to end up with this expression where it's a root 5. And so luckily, because it ends in 5, we can see this here is going to be a multiple of 5. And so 5 multiplied by something gives us 245. So if we take 245 and divide it by 5, we're going to see here that we can split 245 into 49 and 5. So we can rewrite this root 245 as root 49 root 5. But of course, you know full well now that root 49 is 7. And so the integer a was 7. Pardon me. We've now arrived at the expression we wanted to arrive at. It's in the form needed, a root 5, 7 root 5. So we've done question 4, and we've completed the warm-up. Let us now consider another useful form of the equation of a straight line. Okay, so we have the standard y equals mx plus c, which is age-old. You probably saw that when you were like 13, 14, maybe even 12, I don't know. But if you've not seen y equals mx plus c and you're doing an A-level, I think you must be either lying or maybe you're asleep during those several million lessons you had on it. Anyway, let's just think about another useful form, which you may have seen, you might not have seen. So I'm going to start off by just saying that we can define a straight line from taking one specific fixed point on that line, let's call it x1, y1, and the gradient m. So rather than defining a line using the gradient and the intercept, in fact the gradient and the intercept is using this form, okay? Because the intercept is the fixed point. So what if the fixed point wasn't just the intercept? It's like an extension of that from not just the intercept to any general fixed point you might happen to know. So what you do need to know is you need to be able to consider how you could work out the gradient between the point you know and any general point. So if you have a specific point, how could you find an expression for the gradient that links the specific to the general? So first of all, let's just picture this on a diagram of a straight line. And so x, y is just any general point which can slide up and down on that line. So x and y is just any general point on that line. x1, y1, that's the specific point that you know about. And so if you imagine working out an expression for the gradient between these 2 points, well, what would we need to do that? What we'd need first of all is an expression for the distance between the y values. So between y and y1, this height or this difference is going to be y minus y1. In a similar way, to work out an expression for the difference in the x direction between x and x1, our known point, that's going to be x minus x1. So now we now have these two expressions, y minus y1 and x minus x1. We can remember what we mean by the gradient. So the gradient of any line, or this line segment between xy and x1, y1, is defined as m, which is the change in y over the change in x. And in this case, the change in y is y minus y1. The change in x is x minus x1. Now we've got that, we can just make one tiny alteration, a slight rearrangement, and we've got another very useful and powerful form for the equation of a straight line. So as I say, once we rearrange that, we can end up with y minus y1 equals m brackets x minus x1, where y1 and x1, they just represent the coordinates of any point on that line you just so happen to know. So if you know any point on the line and the gradient of that line, that's your way into working out an equation of that particular straight line. Examiners will often like to give you questions where you can't just rely on the standard y equals mx plus c. They make it very hard for you to use that in some instances. So this form is often more useful than y equals mx plus c. And don't get me wrong here, y equals mx plus c also has its place in the A level, but at A level you need to expand and go beyond just y equals mx plus c and have a few more different definitions and types of equations for straight lines in your repertoire ready to use. So on that note, let's have a look at a worked example. So this worked example, we're given a straight line that has a gradient of 5 and it passes through 4, 9. Give your answer in the form y equals mx plus c. Okay, well, you could sort of work back. You could take the x-coordinate 4 and work out sort of like long-windedly. Go back 1, go down 5, and so on. You could get the c doing that way, but I want you to just move away from being too resistant to using this new form. So let's introduce it now. So let's first of all work out the form of a line using y minus y1 equals m brackets x minus x1. In other words, what we had from before. Let's use this and apply it. So y1 is just the known y-coordinate of a point we know. So we know this point, and the y-coordinate was 9. x1 is a known x-coordinate, and we know for this point that the x-coordinate is 4. And so we can substitute in these values. In fact, more than that, we're also told that the gradient is 5. And so we can just pop this in for our value of m. So just substituting in these values, we have y minus 9 equals 5 brackets x minus 4, because our y1 was 9, our gradient m was 5, and our known x-coordinate, x1, was 4. So now we've got that, just expand and rearrange. So y minus 9 equals 5x minus 20. Add 9 to both sides. We get that y equals 5x, and minus 20 plus 9 is minus 11. And that's all there is to it. Ta-da! Let's have a look at another one. Come on, we're on a roll. We're at example 2. Find the equation of the line that goes through the points minus 3, minus 8 and 7, 22. Give your answer in the form y equals mx plus c. Well, here we're not told the gradient, but luckily we can work out the gradient, can't we? Because all we need to do is realise that the gradient is the change in y divided by the change in x between any two known points. And so, using a sketch or not, it's up to you, we can work this out. So I'm going to choose to sketch this. And so if I just think about minus 3, minus 8 down here, and the other point on the line up here is 7, 22, then we can work out the equation of this straight line by first of all considering the distance along the x direction and the distance along the y direction. In other words, our first step, our way into solving this, is to work out the gradient of this line. So 7 minus minus 3, this distance along is 10. And 22 minus minus 8, this distance in the y direction is 30. If you're thinking, well, this distance here looks bigger than that, yes, I know, I'm useless at sketching, but my get out of jail free card is, it's a sketch, the scale doesn't really matter. Okay, if you really feel happy about it, I could even write here, Mr. Bailey's sketch is not to scale because he's rubbish. But I'm not going to do that. I'm not going to do myself down. Positive mental attitude. Anyway, so enough rambling. Let's work out the gradient. So for this line, the gradient m is a change in y, which is 30, divided by the change in x, which is 10. 30 divided by 10, last time I checked, was 3. We now know not just one, but 2 points on the line. So we can take our pick. Okay, so in fact, what we could do is we could just use the classic y equals mx plus c and sub in either this point or that point. Now this point has positive values. Generally speaking, positive values are easier to work with, so let's go for this one. And so let's pick y as 22. So let's substitute in 22. So 22 equals m, which we worked out is 3. So we're saying here that m is 3. I'm going to use u. Times a known x coordinate. Well, we knew x here was 7, so let's use 7. And then plus c. So 22 equals, well, 3 times 7 is 21, plus c. So 21 plus what gives us 22? Fairly obviously c must be 1. So we worked out the gradient, we know now c. So therefore the equation of this line is y equals 3x plus c, in other words plus 1, because c is 1. And now, like I promised you earlier, I'm going to do some past paper worked examples with you. So this was from a past paper a while ago. So the first bit of this question might seem very familiar. The lines y equals 4x minus 7 and 2x plus 3 minus 21 equals 0 intersect at the point A. Okay, I'm going to just remind you now, that was in the warm-up question 3. I'm going to return to that in a moment. So that warm-up question 3 was actually a smaller part from a much bigger question. It then goes on though. We've got this new point B, which has coordinates minus 2, 8. Find an equation of a line that passes through the points A and B write your answer in the form ax plus by plus c equals 0. That's a new form, isn't it? Where a, b and c are integers. So I'm going to remind you of warm-up question 3. If you remember, we had this in warm-up question 3. We got the coordinates of intersection between these two lines was 3, 5. So rather than making you do the legwork all over again, just use this as a shortcut. And hopefully now you can also see the relevance of the warm-ups we do. All these are geared to help you tackle real questions. So we can say that A is 3, 5. And B, we're told what B is. B is minus 2, 8. So what we may as well do now, because we want the equation of a line that passes through A and B, let's work out the gradient of a line that goes between A and B. So let's work out the gradient as we go from A to B, or from B to A, it doesn't matter. So let's take the y-coordinate of B, which is 8. So the change in y from B to A is 8 minus 5. The change in x, minus 2, minus 3. So 8 minus 5 on top, that's going to give us 3. Minus 2 minus 3 on the bottom gives us minus 5. 3 divided by minus 5, that's minus 3 fifths. So that's the gradient. So we also now know 2 points on the line. And so we could pick whichever point we fancy, to be honest. We could even pick, let's just pick A for ease. A's got coordinates which are positive numbers, so let's pick A. So now what we can do, in fact, I'll scrub that for now. Let's use y minus y1 equals m brackets x minus x1, just to get more familiar with this new type of equation of a straight line. And so we're going to use A. So let's say our known y-coordinate is 5, our known x-coordinate is 3, and the gradient, which we've just worked out, m, is minus 3 fifths. So just plug in these values. We get y minus 5 equals minus 3 fifths, x minus 3. Again, just to remind you, because the known y-coordinate was 5, we worked out the gradient, m was minus 3 fifths, and the known x-coordinate was 3. So we want this equation, not in this form here though. We want it ax plus by plus c, where a, b and c are integers. In other words, we don't want any fractions. On the right hand side we've got a fraction with denominator 5. So what I'd suggest to get rid of that fraction is to just multiply both sides by this denominator. So multiply the left by 5 and multiply the right hand side by 5. So y times 5 gives us 5y, minus 5 times 5 is minus 25. Divide by 5 times by 5, that's going to cancel, so we're just going to have minus 3 brackets x minus 3. So second step, we can expand this out. Minus 3 times x is minus 3x, and minus 3 multiplied by minus 3, minus multiplied by minus gives us a positive 9. Final step, get everything onto one side, so the other side is equal to 0. So if we add 3x and subtract 9 from both sides, we get that therefore 3x plus 5y, and then minus 25 minus this other 9 gives us minus 34 equals 0. So that was quite a big question, worth a lot of marks. Imagine if you didn't have this beforehand. So it's just one mark at a time. Nothing is too onerous, just takes a while. It's a case of putting the pieces together to build up a question which is worth an awful lot of marks. I think from memory, this one was actually either a 6 or 7 marker. So these straight line graphs can really pay off if you know them. Let's have a look at another one. So this one, past paper worked example 2, we have a line L1 passing through the point 9 minus 4, and it has gradient of 1/3. Find an equation for L1 in the form ax plus by plus c equals 0, where a, b and c are integers. So again, what we can do is use the general form of the equation y minus y1 equals m brackets x minus x1. Now, I keep writing this out in inverted commas. When it comes to your exam, you don't have to do what I'm doing here. All I'm doing here is writing this out so you can understand the next line in my working, so you can understand a bit clearer, I hope, where my numbers are coming from. So you could start by just writing this next line now. But using this form of the equation, which is sort of in the background, this is where it's coming from. y1 and x1 are our known y and x coordinates on our known point respectively. So because we've been told a point and we know the gradient, this is why we're using this form. So the known y coordinate is minus 4 and the known x coordinate is 9. Okay, so using this form we can now substitute in these values and including the gradient, of course, which is 1/3. We can say we've got now y minus -4 equals m, which is 1/3, brackets x minus 9. Again, adding a bit of colour to proceedings. y1 was -4, the gradient was 1/3, or is 1/3, and x1 is 9. So let's just neaten this up. So minus -4, that needs to be gotten rid of before we make a mistake with these negatives. So that's y plus 4 equals 1/3, brackets x minus 9. We need it in this form. This form has no fractions, everything needs to be an integer. So what I'm going to suggest is we take this form of the equation here and we just multiply both sides by 3. If we multiply both sides by 3, this will get rid of this third here. So y plus 4, if we triple that, we're going to get 3y plus 12. And to keep the balance, obviously we need to triple this side of the equation here. 1/3 times 3, this fraction's undone, we just get x minus 9. Therefore, if we rearrange, if we subtract 3y from both sides, we get x minus 3y, and then subtract 12 as well. Minus 9 minus a further 12 gives us minus 21 equals 0. Part B of this question, the line L2 passes through the origin 0 and has gradient minus 2. The lines L1 and L2 intersect at the point P. Calculate the coordinates of the point P. So let's just think about what L2 is. So we're told a few bits about L2. First of all, it's got gradient, no, not first of all, it passes through the origin. Okay, so the y-axis intersect is 0. So we can use the form y equals mx plus c. The gradient's minus 2. And the intercept is 0 because it's going through the origin. So L2 is just simply y equals minus 2x. L1, we worked out what L1 was before. L1 was this here. So L1 is x minus 3y minus 21 equals 0. There's a few ways we can proceed now. What I'd suggest doing is realizing that we can substitute in y into L1. Okay, because we know that y is minus 2x, we can pop that in for y in this equation here. So moving forward, what we're going to have is x minus 3 lots of y, where y is minus 2x, plus, whoops, not plus, minus 21, sorry, equals 0. And again, if you're not sure where that minus 2x came from, just to remind you again, it's come from the fact that we're subbing in y is minus 2x because L1 and L2 are going to intersect. So let's neaten this up. So x minus 3 times minus 2x, that's going to be plus 6x. Minus 21 equals 0. X plus 6x is 7x. Add 21 to both sides. 7x is 21, so therefore x is 3. Now we know that x is 3, we can substitute that into y equals minus 2x. So x is 3, so sub in x equals 3 into y equals minus 2x. Then we see that y must be minus 2 lots of 3. Minus 2 times 3 is minus 6. I was hoping to get it all on this page without having to move a screen, but I'm going to have to wave my white flag and admit I need a bit more space. So, never mind, I'll acquire a silent inwards tear. So we know that the point of intersection now at P must be when x is 3 and y is minus 6. And that's all there is to do. We've worked out the coordinates of P, so the question's complete. Lastly, another worked example from a past paper worked example 3. We've got a straight line, L1, passing through the 2 points, minus 1, 3, and 11, 12. Find an equation for L1 in this particular form again, where A, B, and C are integers. What I'd suggest we do is to work out the gradient of the line, and then we can take it from there. We know 2 points, so let's just work out the gradient. Seems a fairly natural thing to do. If we can work it out, may as well work it out. So the gradient is the change in y between these 2 points, so 12 minus 3 is a change in y, divided by the change in x. 11 minus minus 1. 12 minus 3 is 9. 11 minus minus 1 is 12. 9 over 12 simplifies to 3/4. We can then use the form of the equation y minus y1 equals m brackets x minus x1, because we know not just 1 point but 2 points, and we know the gradient. So I'd suggest using the simpler point for what to substitute in. It's entirely your choice in terms of what you pick. I'd always go for the positive numbers. However, these are smaller numbers, so it's quite hard to decide. In fact, just for the hell of it, let's go for this one, minus 1, 3. So the known x-coordinate is minus 1. The known y-coordinate we're picking is 3. And the gradient we've just worked out is 3/4. So if we sub in those 3 numbers, we have y minus 3 equals 3/4 brackets x minus minus 1. And we know that because x1, the known x-coordinate, was minus 1, y1 we picked was 3, and the gradient was 3/4. So let's take that and sort it out. We don't want any fractions in this because we want all of these a, b, and c values to be integers. So let's multiply both sides of this by this fraction denominator of 4. So multiply everything by 4 on both sides. Y minus 3 is going to become 3y. What am I talking about? Fool. Y times 4 is 4y. Minus 3 times 4 is minus 12. And then this 3/4, when we multiply it by 4, that's just going to leave us with 3. Then in brackets x, and be very careful, minus minus 1, we need to put plus 1, because minus next to a minus, obviously we know, makes a plus. So if we expand this out, we get 4y minus 12 equals 3x plus 3. Then if we rearrange and get all this onto the same side of the equation, we can subtract 4y from both sides to get 3x minus 4y, then add 12 to both sides to get 3 plus 12, which is plus 15, all equal to 0. So we've got it in the right form, so part A's sorted. We can now move on to part B. We're told that L2 has equation 3y plus 4x minus 30 equals 0. Find the coordinates of a point of intersection of L1 and L2. You could either do a simultaneous equation and solve it that way, or we could use a substitution. It doesn't really matter which way around you do it. What I'm going to do here, just to show you the versatility of different methods you can use, I'm going to show you how you could do this by doing a simultaneous equation. So I'm going to rearrange this one, L2. So we have 3y plus 4x equals 30. I'm going to rearrange L1, so we have minus 4y, just making the y's line up, you see, minus 4y plus 3x. Then I'm going to subtract 15 from both sides to get minus 15. So we could make either the sizes of the x's the same or the sizes of the y's the same. I'm going to make the coefficients of y the same size. Let's go for 12. And so what I'm going to suggest we might do is multiply the whole top equation by 4 to get 12y, and we could multiply the whole of the bottom equation by 3 to get minus 12y. So 3y times 4 gives us 12y. 4x times 4 gives us 16x. 30 times 4 gives us 120. Then on the bottom, minus 4y multiplied by 3 gives us minus 12y. 3x times 3 is positive 9x. Minus 15 multiplied by 3 is minus 45. So, because the signs of these y's are different, if we add them together, they'll cancel. So let's add both equations together now. (12y plus minus 12y), that's going to cancel. 16x plus 9x, that's going to be 25x. 120 plus minus 45, that's the same as saying 120 minus 45, that's going to be 75. If we divide 3 by 25, we'll see that x is going to be 3. So now we know x is 3, we can substitute that into either L1 or L2 to work out the corresponding value for y. So it's entirely your choice now. What I'm going to suggest we do is we sub in x equals 3 into the equation for L1. Doesn't matter if I picked L1 or L2 actually. So for L1, we get minus 4y plus 3 times x, so 3 times 3 equals minus 15. So minus 4y plus 9 equals minus 15. Minus 4y equals minus 24 if we subtract 9 from both sides. Therefore, if we divide through by minus 4, we see that y has to be 6. So we've got that x is 3, we've got that y is 6. So we're done. So therefore, L1 and L2 are going to intersect at the point where x is 3 and y is 6. And we're done. So that's all the worked examples I'm going to show you today. The next thing I want you to do is to try some of these yourselves. So in the books, if you can, I'd like you to go to page 94 and try parts of question 2 and question 3 from exercise 5C. Once you've got those sorted, move on a couple of pages to page 96 and try the below exercises, the below questions on 5D. So questions 4, 5 and 6, question 8, jump on to question 10, and then questions 15 and 16. And as ever, use the book to self-assess and see how you're doing at regular intervals. Don't just work through like a mad person and then only check your answer at the end. Check yourself regularly. If you get stuck, ask a classmate. If you're really stuck, ask me, either in class or even on an email. I'll do my best to get back to you. So keep working hard, keep tuned on the channel, and you'll hear from me again soon. Take care and bye for now.